So today, we'll sort of talk about training-free approaches for image inversion and editing. So we'll continue from where sort of Litu left off last time, but I'm going to do the following. So I'm going to talk about two methods. First, for posterior sampling with diffusion for stylization and personalization. I was then planning to actually do RF inversion, which is for flow models posterior sampling. I decided this morning not to do that instead and wrote up, I thought I should do flows more carefully. So I wrote up a set of notes this morning. So it's likely to be buggy, but nevertheless, I will sort of work through that. And then maybe next time I'll come back to RF inversion. So basically what I'd like to do is RB modulation. I'll talk about what it is. Then CFM, conditional flow matching, deriving everything about that. And then coming back to RF inversion. Okay, so that's my plan. And so you don't have any of the notes for this yet, but I'll post it after the class. Okay. So these things, the RB modulation and RF inversion works, which I'm going to be talking about, is co-authored with several people from Google Research and Google DeepMind. And Litu here was the lead author on this, with Constantine here and several others there. So including from Yuzhuo Chen, Nathaniel, Vincent Chu, and Abhishek Kumar. So this is the same image that you saw last time. You know, the inverse problem, we have seen this multiple times. You've got a blurry image, and you want to get back to P data. Okay. So I'm not going to talk about this as a talk, but I will sort of do it as a lecture. So, you know, we'll just sort of use these slides as talking points effectively. And you saw all these kinds of things yesterday. In the previous lecture, Litu talked about all these kinds of example inverse problems. So let me just sort of move forward and talk about new stuff. The types of problems we talked about last time were effectively, you know, image to image. You give blurry image, missing parts of the image, and you want to do something to the image. But you could do other kinds of things as well, which is you give a text input and get a particular output. Well, this you could say is, in some sense, generative models today could do this directly. That's how they're being trained. They're text guided in any case. Okay, so even though you can think of this as some sort of a posterior sampler, in a sense, this goes back to the discussion we had just before we started. These are the model is already pre-trained to be such samplers. Okay, you could think of this as posterior, but not, or you could just think of it as a model which is guided by this kind of a thing. Okay, but a posterior sampling question here could be a personalization, meaning you give this thing and then you give an additional image and say you want to extract this style and you want to generate consistent with this style, you want to generate this. So this would be a test time optimization. So this goes back to your discussion. You could say this is the pre-trained part of it, and this could be the test time optimization part of it. Does it make sense, Constantine? I mean, this just goes back to the discussion you had. I think I'll keep that recording actually in the. I'll start from the beginning. It's just useful for people to hear that too. Okay. Yeah. So, or you could do other things, which is content style composition. So this is the style, you want to extract this style. This is a picture of a dog, and you want to combine, you want a sample which is consistent with this style, this content, and so this is what you would get. Okay, so, and this text. So, we'll talk about algorithms for doing these kinds of things today. Okay. So, what are the scale of these models? And this is going to become important when we talk about algorithms and taking gradients and so on. Okay. So about 3 or 4 years back, stable diffusion, which really got the entire academic community and to start thinking about these kinds of problems at scale was about a 1 billion parameter model. Today, the models are about 10 billion parameters. So these are sort of rectified flow, RF rectified flow models. This is sort of still a diffusion model, but we saw from the last few lectures that this separation between what a flow model is versus what a diffusion model is really about nomenclature more than anything fundamental. Okay. And today we'll look at that even more carefully, where we will go through the flow model yet again using something called flow matching. And we'll see that again, you'll see it's analogous to it's just another way of thinking about the same object finally. Okay. So the posterior sampling problems with diffusion we want are, you're given some such thing, call this y, and you want to sample an x consistent with this. Fine. And so what is the story at this point? Well, from last time, we know that you need to get a conditional score. If you can run a diffusion with this, then you're in business. You don't know the conditional score. So what would you do? You would basically use Bayes rule, look at the unconditional score. There's a correction term, which is the conditional of the measurement, consistent with where you are in the diffusion. That's the correction term. This is unknown, and we need to approximate it in some manner. Okay. Last time we saw DPS approximation. Litu talked about it. Maybe I'll talk about it once more, just so that we get all the notation. It's worthwhile to think about it. Constantine, you wanted to say something.
Y is equal to a known operator A of X.
Good. I will always be in today's setting where the operator is known. The relation between the measurement and the quantity of interest can be mapped through some differentiable operator. That's sort of the assumption which I'm going to deal with.
What that means when Y is text.
So this goes back to what I think is several.
Classifier, I could put something there, but is that?
You could use clip or something like that to align, right? Then you could go, but I'm really not thinking about text here. I'm thinking about image-based style. But you could think about sort of guidance that way through.
What does it mean? What is A?
Good. I will talk about that. So I will talk about exactly what it means for style in that case, in that context.
So let's kind of set this up, even like for these.
I will, but I'm going to sort of wander about several topics before I actually get to that. So yeah, Jacob?
Really, the forward operator is when it takes the ground truth image and gives you your measurement.
Correct.
The ground truth image is gold-plated dog, and then I can get realistic dog. Like, isn't that already kind of like a posterior sampling? Like, then that seems like that is a version of stylization.
No. The forward operator in this case will take a gold-plated dog and give the word gold. Melting gold. It'll give, that's what it is. It'll give a vector which encodes that. There are a bunch of measures. So that's why is actually in that example there are three different things. You have to deal with them somewhat differently. Okay. So the example I was talking about is pure stylization. Just say there's a text of a dog, and the pure stylization is I give you that rose image, just the text of the dog, and then you generate any dog which is in that style. That is pure stylization. In that case, what is the forward operator? The forward operator in that case would take an image and give a vector, high dimensional vector, which somehow, it'll do the following. If I take two different images, both of which in the melting gold style, then the output of this forward operator will be very close to each other, irrespective of what that content is. That's what that forward operator is. Okay, it's not giving you a text; it's giving some vector embedding of of style. Sorry?
And if I give it any two gold-plated dogs, then it.
No, if I give, even more than I give it a picture of a gold. It's not gold-plated, but whatever. This whatever melting gold is what I think this is called. So give an image of a dog in melting gold style and give an image of the rose in melting gold style. Both of them should have similar style. It doesn't matter whether it's a dog or a rose. So in this way, these are multiple measurements. How do you sort of combine multiple measurements is a different story. I'm just talking about if I give you a single measurement. Yes. Correct. That's basically what I mean here. Okay. But let's go back to DPS because you saw this thing from the notes. Let's actually just talk through this. I know that Litu talked through this last time, but it's worthwhile to just see it written out because it's in the notes. I may as well as go through this business once more. Okay, so you recall what DPS was. It's an approximation to find the conditional score. Okay, meaning we want to figure out this quantity, grad log pt of xt given y. So I given, so this is the score needed to diffuse given a particular measurement. So using Bayes rule, you can write it as grad log y given xt plus grad log pt of xt. The third term goes away because when I take the gradient, the normalizing term disappears. So what now look at grad log of y given xt. That's the gradient of log. Now look at the density p of y given xt. I can further conditioning on x0 and uncondition on it with just some total probability theorem. Okay. And now this is nothing but the density of y given x0 and xt. This is the clean image, this is the noisy image. But the measurement is a function of the clean image. You don't need this. It's a Markov chain at this point. So this goes away, which means that this is, I can just replace this term by just p of y given x0. Okay. And so now you can look at this as the following. This is the variable. In this case, I will treat this as a function and this as a density. So then I can treat this whole thing as an expectation with respect to this distribution of this function. Okay, where this function, y is fixed here, remember. The only variable here is x0. So this is my random variable here, and I just treat this as a function. That's all there is to it. And then, so that's what this, so you can think of this as some g of x0, this whole, if I think of this as g of x0, then this is nothing but the expected value of g of the random variable x0. It's for a fixed y. And now I can do a Taylor series expansion. If I do just the first order expansion, it is nothing but the expected value of x0, which means the expected value from this conditional distribution. This is the what is this conditional distribution? If I'm at some point xt in the diffusion, if I were to run the diffusion all the way through to get an image, I'll get an x0. Every time I do this, presumably I'll get for a particular latent xt, there's a distribution over the image manifold, and there's an average over that. And note that this expectation in general may not even lie on a manifold. So this quantity, if I sample this again and again, let's look at this. If I sample from this distribution, oh sorry, now can you? If I sample from this distribution, fix an xt and sample from that, each time I sample it, I'll get a valid image. Okay, that's what this is. But when I take the expected value, from the appropriate conditional distribution, this quantity may not be a valid image. Okay, because the image, the manifold may, unless it's a linear, the space is linear. All right, but what we could do here is just to do a Taylor's approximation, which is for any x0 image, you can write it as the average. So this is not an image, but this is sort of a blurry image, plus all the correction terms to deblur it, essentially. Okay. And if you now take an expected value of this, well, then I push the expectation here. This first order term goes away because this is some random variable minus mean. When I take the expectation, this goes away. And therefore, the approximation is I'll just push this expectation all the way inside the function. This is the Jensen gap, which is what was talked about last time. Okay, so this is the DPS approximation. The useful thing here is that the mean can be computed rather easily. Why? Because the mean, the conditional expectation of x0 given that at that I'm in the diffusion at stage xt is an MMSE estimate. And Tweedy's formula says the score is an affine transformation of the MMSE estimate. This is super useful because previously we used this relation to say, hey, I want to learn this score using the MMSE, by reformulating an MMSE and then getting lots and lots of samples and figuring things out. Now we're going to do it backwards. We have already learned a score and we need this MMSE estimate. So we'll use the score to compute the conditional expectation. Okay. So this can be now directly computed by one pass through the denoising network. Okay. And that's basically the DPS approximation. Okay. You use the Tweedy's formula. You can now, you know the score. So using that score, you can compute the conditional expectation. And once you have that, then essentially you can approximate the measurement posterior, essentially. I mean, given I have the measurement y and I want the conditional expectation of the measurement, the grad log of the measurement given where I am in the noisy diffusion, that can be approximated by one call to the score network and then sticking it into this expression. And this expression is known now. Why do you know this? Again, this goes back to the discussion we had. The relation between y, the measurement, and what the signal is some known operation. So you can take a gradient through that function and get this to be done. Okay. So this is essentially the DPS approximation, which Litu talked about last time. I just recapped the same thing this time. Yes. Good. How do you do this gradient with respect to xt? So this thing here. So xt is in here. So you have to back propagate, use chain rule. You have to back propagate through the score network to the input of the score network. Okay. So that's right. You have to back propagate through the measurement operator and through the score network to the input. Does it make sense? So it's just chain rule. You're not learning any variant of the score. I now in this part of it during test time. So in the training time, we were trying to learn the score network. In the test time, I'm assuming I have a black box that does this. So now I need to compute this for an appropriate value of xt and sigma. I know this relation. This is what is here. So I need to take a gradient. So how do I do that? I'll back propagate all the way through. That's all. There is no learning of any sort here. It is just chain rule essentially. That's all is happening here. Make sense? Okay. This question is good because it's important. But we are going to see that this is actually this is really the problem with. So Litu talked about PSLD, STSL. This is the problem. What do I mean by this is the problem? If you're this is a model size, 4 billion or 10 billion parameters. So you're backpropping through such a model, and that can be expensive. Okay. And I'll show you some numbers to tell you what expensive means in a few minutes. Good so far? Yeah. But despite this paper was very important. So this DPS is a paper by Chung et al. This particular paper, and it's been very influential. Okay, this is an important paper because this, for the first time, allowed us to think about these kinds of problems, inverse problems, in even as an approximation with these powerful diffusion models that just emerged. And so a lot of work has built on this particular work. Okay. So let's go back to the main story. So given this background on posterior sampling, now we are all caught up. So we know one approach to deal with this problem. We needed to diffuse where we know the score. We had this y given xt, and now we are using the DPS approximation or PSLD or STSL or whatever else to approximate this. Can we do something else? And so that's what RB modulation is. It's again a training-free approach, and the key is that it avoids backpropagation through the score network. Okay, that's what is going to make things cheaper. Now you see where the backpropagation through the score network came in the previous things. Okay, question.
Yeah, why is that so bad?
Why is good?
I mean, that's
Very, very good question. Why is backpropagation through a score network hard? Here are some numbers. Okay, let's look at some numbers. Okay, so if you want to let's look at various things. These are all for A100. Okay, that's the number that's the GPU for all these things. If you want to do what Constantine originally suggested, take a few samples, just fine tune your network. Okay, you got a network, take 10, 20, 10, 20 samples and just train it. Now you have a pre-trained model. You have that is already a base. Now I want to fine-tune that pre-trained model for a particular stylization. Just to be concrete, let's say stylization. I get a bunch of stylization thing. Maybe I'll do LoRa, I'll do something else. Maybe I'll do full fine-tuning. Now I need to, so this is order of tens of samples. If you just take one sample and try to fine-tune it, you could lose basic features because you are giving so much weight to that whole thing, right? So you need a reasonable number of samples to actually fine-tune this reasonably or fully. And the fine-tuning could be LoRa fine-tuning or it could be full fine-tuning. Fine-tuning, what does it mean? It means it's fine-tuning with respect to the parameters of the model. And so your gradients are with respect to weights. Okay, it roughly took about 20 minutes per style for LoRa fine-tuning for a particular, on a A100 GPU. Okay, and if you want to do full fine-tuning, it'll be several hours. Okay, just to get some numbers on this. I think this is what you are asking, right? Something like this. Now you can do any of this back propagation through a score network. So DPS, PSLD, P2L is an algorithm for a different group, STSL, all these kinds of things. One sample is enough. That's what the advantage is because you're doing a test time optimization. And the gradient is no longer with respect to the parameters of the model. It's with respect to the input to the model. Okay, the X sigma there in that example there. That's what the gradient was with respect to. And this with a 1 billion size model, which was like stable diffusion size model, it took about 10 minutes for PSLD to actually generate one image. Okay.
DPS would be way more because we're doing it in pixel because X.
Yeah, so yeah, you need to first train a large model at scale. Yeah, first of all, you need a massive model and then do that through that. Exactly. That's what PSLD is. PSLD is doing in the latent space of stable diffusion. God, why somebody is blocking me out? To get back, test time. So we talked about full file. This is training based. This is with a latent diffusion model. It takes about 10 to 20 minutes per image. Okay, and this is really because at each step in the diffusion, as you're getting towards the image manifold, you need to backprop through the measurement, through the score network, right, all the way through. Actually, it needs to go through the VAE through the autoencoder as well to the latent space. So it starts from the measurement spaces up there. You need to go all the way through. Okay, but a big expensive part of it is through the score network. And so for stable cascade style size models, you'll see that what you can do is to reduce the time significantly to about 40 seconds per image, because you will not need to do a backprop through the score network. And we'll talk about what the algorithm is in a few minutes. But does this? I haven't told you the method, but I've told you sort of the costs involved in this business. Okay, so what is RB modulation? It's an algorithm for posterior sampling. It has two pieces. There's an optimal control aspect to it, and there's a transformer engineering aspect to it. The transformer engineering is called attention feature aggregation. I'm not going to talk about that. You can. It basically is to deal with the question Jacob was asking, because there are two separate things. There's content and style. How do you disentangle this thing? And that is essentially cross-attention engineering of certain type. Okay, so I don't want to talk about that. I want to talk about sort of the class's main thing, which is about how do you sort of modify the drift field. And so that is the stochastic optimal control part of it.
Given a vision network.
Yes.
And you're just gonna do some modification. You're not updating
anything. You'll update the attention weights. You can do some engineering inside the network without backpropagating. Okay. So that's a separate engineering piece. By just extracting some weights and just putting it into the transformer in the inside of the network. Okay, that part I don't want to talk about. I want to talk about the clean posterior sampling point problem here. Okay, but if you're interested in that, I can sort of talk about that offline. Okay. So let's go back to the posterior sampling story. We needed this. Wrote it as base rule as a sum of two terms. There's a basic drift, a basic score, and there's this conditional thing. Instead of saying I'll try to learn this or any such thing, let's just say we'll just replace this by any function you want. Nice function. Okay, let's call this a control. But what should it satisfy? Well, by the time you get to the terminal state, so time is going forward, and by the time time goes to 1, whatever you end up with should be consistent with the measurements you get. Okay, so you can put a terminal cost saying that you choose a function u. At each time you can update your function in some manner, such that by the time you have reached the image manifold, the image you get is consistent with the measurements, and G will specify what that consistency means. Okay. You can look at this, so you can just think of this as an optimal control problem. Now, find a control U such that this is satisfied. And now, what is this U? Choose something nice. And what do you mean by something nice? Put some cost on the trajectory, a convex cost. Here it's a quadratic cost, but you could choose some whatever convex cost and put it and say, I want to solve an optimal control problem. So this is another way of thinking about exam. So far, we have done nothing except just thought about this as a control problem. That's all. We took the same posterior sampling problem and said that it's equivalent to a optimal control problem. Okay, with a terminal cost, which depends on the posterior condition you have. Is this making sense so far? Okay, if you have this, first let's see what we can do with this kind of stuff. Okay. Suppose now, let's look at the simplest setting. The data distribution is Gaussian. Okay, and all the the drift and the diffusion coefficients are all affine in this state, like an OU process, for example. Okay, there's no non-linearities anywhere. Then something called certainty equivalence holds in the following sense. Okay, so we want to solve this optimal control problem. This is a stochastic optimal control problem. Okay, it's stochastic in the sense that I give you a minimization with specifying a dynamic. The dynamic has something which is non-linear in the state, something else. But suppose I say all these are affine or linear. Okay, then certainty equivalence says I can instead solve an optimal control problem where I forget stochasticity. I'll solve a deterministic optimal control problem. Okay, the same problem with deterministic thing. But this is only when linear. Everything is linear. P data is Gaussian. So very, very restrictive setting. But once you have this is now in the HJB story. You can solve this using minimum principle or whatever you have. Classic optimal control maybe can be used to solve this problem. Okay, and if you solve this optimal control problem, you will get a controller which will depend on. It says that if you're in state time t xt, this is the way you should go. And you want to go to a measurement y1, it tells you that the drift field that is needed is this. Okay, so this is assuming it's all linear. First of all, that the style extractor is a linear map. That's not true. Okay, but this is really, really stylized, just a toy problem to essentially tell you what the storyline here is. Is this making sense so far? Okay. Now the question is what is in reality? Of course, there's no style extractor matrix A. Okay, it's something called the CSD, the contrastive style descriptor. I forget the lead author's name. Gautami, maybe? I forget her name. This is from Maryland, Tom Goldstein and his group. So it's yes. Yes. This
Except for the initial condition.
even initially I put xt0 equal to x0. So this whole thing is a deterministic problem at this point. This is just a standard. That's why I was going through the certainty equivalence discussion. So I had a stochastic optimal control. If the SDE is a linear SDE and the P data is Gaussian, then certainty equivalence holds. I can forget the stochastics, solve a deterministic optimal control, and that same control is optimal for the stochastic system. This goes back to 1970s, 60s. This is classic control from that era. Okay, I don't have a better attribution right now, but okay. So you can solve this control problem, and you know this thing. Of course, this is stylized. For practice, we don't have a linear thing. We have some style extraction network, which is called the contrastive style descriptor. And as I discussed with Jacob earlier, that it's basically a network. I think they fine tune a clip essentially to get this CSD. They essentially, you given an image, use the stack to actually get a vector which describes style. And if you want to compare two different images style, send it to this network, and it's going to give you a score, a vector score for each.
Just some differentiable box.
That's all. It's just a differentiable stack. I think it's just a clip stack, if I'm not mistaken, but somebody can correct me if I'm wrong. It's a fine-tuned clip stack. Okay, so here the control was, we just said it's u dt. But we are not really controlling everything. We are controlling a correction to the score. Go back here, you see that. So the control is not this, it is this plus this. So you could try to solve some other problem as well. And the reason I want to talk about it will become clear in a second. So you want a u. In a Gaussian case, what does the score look like? It's affine xt. Okay, so this is just linear. So in which case, this motivates this following other optimal control problem. Okay, x plus u dt. It's a different dynamic. And you want to minimize this cost subject to your terminal constraint. Okay. Again, you can solve this, same thing. This is minimum principle. I mean, this is a classic optimal control problem. You can solve, you can write the HJB equation. You can solve this using the minimum principle or whatever you want. And what you're going to get is a closed form solution to this. But look at this closed form solution. It requires you to know x1 as well, not just y1, not just the measurements, but knows you the x as well. But that's the whole point, right? We're using diffusions to actually figure out what x is. But the optimal controller requires you to know x at every stage. So a plug-in estimate for x would be conditional expectation. That's the box we always have, Tweedy's formula. So instead of x, you plug in Tweedy's formula, conditional expectation of x given x1 given xt, and use this, something might happen. Okay, but even this is, the structure of the solution is very specific to this particular optimal control. You change the data distribution is not Gaussian, but all this stuff is telling us, is motivating sort of a practical algorithm, which I'll talk about next slide. Correction. I'm going to talk about an impractical algorithm in the next few slides, and then I'll talk about a practical algorithm. Okay. So first, let's start with a one approach for solving this problem. So at some point t in the diffusion, I've got an xt. I need to figure out where to go next. Okay. So what do you do? Well, we'll perturb xt by some u. We'll set u to be 0. So I'm at some diffusion. I'm at some point in this, at the xt lives, quote unquote, in the teeth noised manifold of noisy images. Okay, right? It's on that level set roughly. So think about xt there. Okay, you want to perturb it somehow to make it more consistent with measurements. So what do? You take xt, you predict, if initially set u is 0, you predict what x0 would be for this xt, Tweedy's formula. Okay, so x0 bar is nothing but that plus the score. Okay, so it's a forward pass to the score. You've gotten this. Now you've gotten this x0 bar. Let's evaluate how good this is. You got your reference image, the melting gold z0. You got the style extractor network, psi. So you can look at the error between these two, and you're going to get a score for how good your average measurement is. Okay. I will update you here by taking gradient with respect to this, and I can iterate this a few times. But look, let's unpack this box. This is a very expensive thing. We are taking a gradient with respect to this u of this. So I'm taking a gradient with respect to u, which means I need to go through this. This is a squared loss. I know how to take a gradient, but then I need to go through this thing. I need to backprop to this tile extractor. Okay. Then I get to x bar u, which means here, which means where is u coming in here? Well, x hat t is a function of u. So it's the input to this core network. So again, you're backpropping here through this core network. Okay. So each time you do this loop once, you are doing this one. You're taking a backprop to this core network. You do this multiple times. It's going to be that backprop cost. And then but suppose you could do this a certain number of times, you'll get a perturbed state. And then once you've got this perturbed state, what do? You do DDPM or DDPIM. I've got this state X. This is my new XT star. What do? I will guess what X0 is to conditional expectation and renoise it to XT minus 1. This is my usual DDPM pipeline. I can do this using a flow model or a stochastic model or what have you. But essentially, this is what we talked about in theory, where we had closed form. If you didn't have a closed form solution, this would be the immediate operationalization of that idea. Okay? The optimal control implemented in the system would lead to this. It is still super expensive, but at least it tells you how to go from sort of that control formulation to an actual algorithm for stylization and things like that. Okay.
Where was the solution to the specific flavor of terminal cost that you need?
So I'm just taking a gradient step. Good. The terminal cost is coming in here. If I run this to infinity, I'm solving the terminal cost constraint by gradient descent. So the terminal cost is to minimize this cost. Do you see what I'm saying? This was the cost. I need to find a u such that it minimizes this, which means if you assume that the problem is convex and gradient descent actually gets to the right solution, then running this for m to be arbitrarily large number of times would solve this problem. So there are many approximations going on.
The sum of the square of the trajectory cost.
Good. So this will be when gamma is so large. So exactly. It's basically essentially only the terminal cost, and the path cost doesn't matter. So I sort of skipped that limit of gamma because the path was just put to regularize your solution, really, for the optimal control. Really, you care about the terminal cost, and this is basically focusing purely on the terminal cost. Good question, and that's basically what is going on here. Okay. Now you see the connection between what we did previously and this one. Okay. So this requires a backprop through this core network, which is super expensive. So instead, what you can do is prox. What we were doing is optimizing XT, which means on the teeth noisy manifold, you are sort of moving this point around. And the way we were optimizing in that space was, hey, you got something in the XT. I will figure out what X0 is for that, figure out whether that X0 is consistent with the measurements. And then if it's not, perturb my XT back here so that it becomes more consistent with the measurements. Do you agree? That's basically what is going on. Instead of sort of optimizing in the teeth noise latent, you could optimize at 0 itself. What do I mean by that? Okay. Look at this proximal cost constraint instead. Okay. Find me a new X0 so that it is close to what I think it should. So I am at XT. This XT, the prediction of what X0 will lead to is this point. Find an X0 that's close to this, and simultaneously is also consistent. If I just do this alone, you're not going to be necessarily consistent with the measurements. Simultaneously make sure this X0 is also consistent with the measurements. So meaning, look at the style descriptor of your reference image, look at the style of what this X0 is, and look at this error. So now I can do gradients not in the U space, but the X0 space, which is much cheaper because I'm not going through the conditional expectation, which is where the backprop was happening. If if you're moving things around inside the expectation, that's where the backdrop to the score network is happening. Here, that isn't happening. This is the variable, and you are basically just finding a new clean surrogate of a clean image. And once you're happy with something, you can just noise it to level t-1 in one step. Okay, so this is really a prox approximation to sort of the algorithm we talked about in the previous step. And this is what is RB modulation. Yeah. Yes.
Because we're trying to make X0 be close to something that's not an image in this case. Like that.
Right. Well, hopefully as you get closer and closer to the manifold, E of the expectation will, if the manifold is not crazy, then everything should be good. And when you're far away, anyway, it's noisy. Hopefully it's okay. Okay. As I said, this is all intuition. The sort of formal thing ended with the linear setting. After that, it's all intuition driven by sort of what we sort of qualitatively took away from that. Okay, so there are no, if you're interested in proving some of these kinds of things, showing approximation error, they're all open questions. Okay, at this point. But this algorithm actually works at scale. And in fact, it has been productionized by Google. And yeah, it's actually working at scale for, I don't know, whatever Google scale, whatever that may mean. Okay, so, and the reason is the following. Finally, at these scales, it's about 30 seconds per image, which is really fast. Okay, from sort of tens of minutes, you could come down to this. That's basically the prox is essentially allowing, because you're not backpropping to the score network. That's basically it.
The idea is the content descriptors are much smaller.
Yeah, these are all small models, much smaller models. Do you remember the size of these models, anybody? CSD, it's of GPT-2 size scale, you think? The CSD models? I think it's of that scale. That's my, but I don't count on it. I had to go and check back. Okay. So the other thing I wanted to talk about, I'm going to skip the ablation studies and all that because it's there in some talk somewhere. But the other thing I want to take sort of highlight in any of these kinds of things is how do you evaluate how good these things are? Okay, why is one style better than the other? Okay, the gold standard for any of, so you can make up all sorts of numbers. Okay, I shouldn't say. I guess I'm recorded. So you can do all. You can make. There are all sorts of standard metrics for these kinds of things. And you can evaluate things on these metrics. But you can argue about it till the cows come home. I mean, whether this metric is better or the other metric is better. Finally, the gold standard for all this is human evals. And so since this work was with Google, they have a really good human evals team. Okay. So what you do is finally A/B testing. Maybe I can see if there's in the paper somewhere. Let's see whether I should have pulled up the paper at some point. Okay, so what you would do in an A/B test is you'd use a bunch of algorithms, take an image, write a caption, and say which is the best one. Just blind testing with some test group. So user study, what we evaluated here was finally with 7,000 responses to capture human preferences. And so, and I mean, this method, I mean, that's why I'm talking about it, otherwise I wouldn't have, is outperformed at that point all the other benchmarks which were around. And so all this goes into sort of the engineering decision of should this algorithm actually, so there are two things that are important. One is that when you sort of build an algorithm of this type with some principal heuristics, but finally there are no theoretical guarantees, to be honest. Okay? Then why should somebody use this? Okay? There are two things you need to answer. First, in terms of performance. And if metrics also are unclear, human studies at the scale you care about is something important. But there's another thing that's also very important in this game, which is actually I didn't realize till going through sort of all this work. Algorithms that work at some scale just break at bigger scales. So it seems to lots of things are amazing at models of 100,000 size. At a 100 million size, many of the algorithms just flatten out. They're not scale. Either their performance just saturates or the computation or something else breaks. Then at a billion scale, something else happens. So really what these, the Googles of this world do is to actually push it through at scale after scale. And you have to, for an algorithm actually to get into production is highly non-trivial. It needs to work at various scales before they're willing to push. At the bigger scale, it needs to be, it shouldn't crash, it should give reasonable results, it should be fast, and all these kinds of things. So that is something you realize. So simplicity is actually a highly undervalued thing, but it's important because that's the only thing that allows you to scale things through sort of many orders of magnitude. For example, it's not in this case, but in some other setting. If you're trying to do maximum training, forget it. It will not win the scaling wars at some level. Okay, so these kinds of things you just learn by sort of going through this thing. So RB modulation went through all this scaling, tests before it actually went into production. This was 7,000. This study, which you are publishing here, is 7,000 samples, 7,000 human responses. So one is a human. One response is one A/B test by a human. Okay. There are other bigger studies, but they're all synthetic. That's why I didn't put it. It's all in the paper. There are some you can ask FID score. There are a bunch of standard metrics for evaluating these kinds of things. And they're all debatable whether this is the right metric or not, because you can game many of these kinds of metrics. Right? I mean, so, which is why, yes, it's all there, but finally, I think for production. So I wanted to sort of highlight this because there's the academic story and there's the production story, and they're not always aligned. So that's something to sort of keep in mind. Okay, so what can you do with this? So far I just sort of talked about the setting and so on. What can you do with it is these kinds of things. So the quality of images, it essentially allows plug and play solution for stylization and composition with diverse layouts. What I mean by diverse layouts is this dog is facing that way, but you can generate prior methods at that time. Essentially, it found boundaries. The way you could do these kinds of things is sort of find a boundary and then stylize that. But this generative approach, because finally you're separating content and style in some way, right? Because the style extractor is just purely looking at the style, and the content is dealt some other way, which I didn't really talk about here. Okay, so if you can do these kinds of separations, then you can sort of do diverse layouts. Each time you do a random input, you may get something else. Okay, that's one advantage. The second interesting thing is novel styles. So if I want to train images which combine this style and this style, okay, I don't have any examples of this new style, but I could use the methods we talked about to actually do this interpolation. Why? Well, you could alternate in even steps. You could use one style descriptor in odd, or you could use some combination. There are a whole bunch of things you could try. Or half the diffusion, you could try one thing, okay? Or you could use some mixture of these two style descriptors as your loss. You can do all these. There are a whole bunch of things you could try, okay, to try new styles. And indeed, you can combine styles depending on some strength to actually generate novel styles using this kind of stuff. And you see, these are all cheap because it's still just using the same thing with two fees instead of just one of them. Or psi. Is it fee or psi? What is that? Psi. Thank you. So and the world model is the foundation model for all these are really strong. What do I mean by that? If you take images from the wild, so these are things which just images from the wild. Somebody drew this, and you ask, can your model and your method generalize to the wild setting? And indeed they can. This is an advantage not only because of this method, but really also the foundation models are so powerful today that you say, I take this image and generate a house on a mountain. It's amazing what is possible with these kinds of methods now. Okay. So these are the things that are that this method allows. So as I said, it's in production in several sort of platforms, Pixel phones, Chromebook, tablet, and YouTube, and several application settings. So that's what this is on. I have about 20 minutes left. I want to then move to flow models. Okay, so I'm going to give an introduction to the flow models and then switch out of these nodes. And I want to come back to RF one more pass. I think it's worthwhile for us to understand flow models once more, just before we come back and look at this. These samplers are all stochastic samplers. Now I could say, hey, I want to do this kind of inversion and editing, but with flow models. Okay, you could try to convert the flow model to a stochastic model, do this gradients and all that stuff. But if you have a flow model, is there a way to just flow it and do gradient free completely? And so no gradients at all. That's not even RF requires, RB still requires sort of gradient computation in the prox optimization. Can you do gradient free? And if you could come up with a gradient free method for a flow model, it's really powerful because it's fast. You can do it on edge device GPU. You can actually do, I take a picture, I don't want it to go to Google Cloud on my device, I'd like to do something here, can you do that kind of stuff? And so that's what RF inversion, this is another algorithm we developed. That's what that deals with. And this actually also been productionized by Google in various settings. Okay. The combination of RB modulation, RF inversion actually is also sort of in various things like Imagine 3 and things like that have this kind of stuff in it. But before I tell you about this method, I think it's worthwhile to go back and think about flow models again carefully and realize that flow models are essentially another way of thinking of everything we have done so far can be rethought of this way too. They're all analogous to each other, different ways of getting to the same point, but worthwhile to understand all these things. None of these notes, the notes I have, give me 1 second, let me just check something. Yeah. I just want to make sure it hasn't crashed any time since then. Okay, fine. Is it? It says that dot is there on top and there's a rec. So I think it is still recording. Okay, so I want to now switch back to theory and talk about conditional flow matching. All this was diffusion, including RB modulation. It sort of is inverse problems with diffusion models. But I want to now switch to inverse problems with flow models. And so let's think about flow models once more. So as I said, when we talked about RF, I talked about these flow models. This is by Chang Liu et al. On flowing straight and fast. There's Lippmann and collaborators on flow matching for generative modeling, Albergo and Van den Eyden. These are all sort of roughly simultaneous sort of flow models. The notes which I'm talking about here are heavily drawn on this. I really like this. It's a very nice tutorial article, flow matching guide and code. And that's what I based this on. So let's look at a flow view of generation. Okay. What did we do previously? We had a SDE, which we took data, we noised it. I'm just going back to lecture 3. We noised it and got Gaussian. We did Anderson's reversal. We started, and if you use that reverse process, we started from noise and we got to data. This is the whole denoising story we said, right? This was our SDE view, forward and backward SDE. And then we also said its density evolves through the Fokker-Planck equation. And so we could, and if its density evolves through the Fokker-Planck equation, then you can also, the drift is learned through denoising score matching. That was Tweedy's formula, mean square, and so on. Okay, so we know this story. That's the stochastic story. The stochastic story plus Tweedy told us how to learn this score or the drift of this diffusion. And then we said, hey, we can do an ODE version instead, DDIM, again by looking at the Fokker-Planck. And what did we do? We match marginals. We wrote the marginals for this. We came up with a differential equation, that's the DDIM thing, which said the marginals match that of the stochastic system. All the noise was the initial condition. We flowed it and we got this. That was the story. And that's what I've written here. it's basically nodes 3, 9, 15, and so on. Okay. So we are going to do the same story quickly from a different perspective, from a measure transport perspective today. Okay. So you can look at 4 for a much more general description. I have simplified it more than simplify. I've basically looked at special cases. These things generalize much more than the special case I care about, what I'm going to talk about here. Okay. But the goal is the following. At t equal to 0, let's say that there's some distribution P0. I'm just going to assume Gaussian, but there's nothing special about it. I mean, in terms of calculations and stuff, there's things special about Gaussian, but in this setting so far, t equal to 0, draw a sample from a Gaussian. At t equal to 1, I have a sample from the data distribution. Let's learn a velocity field parameterized by theta such that d by dt of xt is ut of theta xt. This is what we want. So I want to find a way to transport x0 to x1 through this differential equation. This is the problem. Constantine, is it?
How, so xt is defined by just noise?
I'm defining xt. No, xt is defined through this. No noising. There is not. This is it. I am going to define x0 as p0 as a sample from p0. Okay.
But you have the word learn.
I'm learning. The learning is in this thing. I want you to learn a mu theta, a field, a vector field, a function, which has a following property. I initialize into this function at time 0 a sample x0. I run this from time 0 to 1 continuously. At time equal to 1, this, assuming measurability and all that stuff, this will return a random variable x1. I want that x1 to be having distribution q star. Okay, this is my problem. So the learning in the sense that I'm going to give you a sample from the 2 endpoints and tell me how I can go from this endpoint to that. That's the learning problem. Is that clear? Okay. So DDIM is in fact a case of this kind of a thing. Okay, it's in this so far I could have said DDIM in this way too. It is a way to transport from x0 to x1, and the u theta was learned by Tweedy's formula. Basically, the way we defined u theta there is saying, hey, I know that the Anderson reversal has this thing. I can look at the Fokker-Planck, make it the continuity equation, then look at the velocity field of that. If I use that velocity field, which we saw was some affine in the score of this thing, grad log pt of something plus something, we had some function there. You use that, it would have this property. Okay? So far I haven't gone outside the DDM setting. So really there are 3 objects which we need to worry about. One is the velocity field. The second is the density evolution. At every point in time, there's a density. And the third is a sample path. From x0, there is some sample path which lead to x1. So there are 3 separate objects. Okay. Here is I've just written the definition. Ut is the true velocity field. Forget about learning we'll come back to learning in about maybe not even today's class. Let's just talk about this picture for the next 10 minutes. I've got a velocity field ut that I've got a pt, a density associated with it, and I've got a sample trajectory xt with x0 here and x1 here. What's the relation between u and p? Well, that we have beaten to death in early classes. That's the Fokker-Planck equation, or the special case of that being the continuity equation. Meaning, del by the time derivative of the density is minus of divergence of utpt. The probability flux, the divergence of the probability flux plus the derivative of the density is equal to 0. The conservation of mass. Okay, that's basically what is going on here. Okay, we did this in lecture 3, 4. We did it again in Markov processes. So this should be this object should be very happy and familiar to all of you now. This is a comforting object to look at. Okay. Yeah. So there are these 3 things which I care about: the sample path, the density evolution, and the velocity field. If things are nice and things are nice, then if I specify any one of them, in principle, I should be able to get the other two. Okay. For example, if I specify the velocity field, okay, then I can solve the continuity equation and learn the density. And then I'm not saying that this is practical, but I'm just saying that this is in principle. Then I can sample from that density function to get xt at any point in time. Okay? So I can go specifying any one of these things. It's a little fudgy. It's not mathematically precise, but because there are all sorts of conditions that need to be satisfied about smoothness and all that stuff. But assuming the world is good, any one of these ABC will give you a full solution. What we did now with this viewpoint is that we specified B. The way we specified the density evolution previously was saying, there's DDPM, the Anderson reversal, that gave me a PT. Now find me a UT that satisfies PT, and sampling from that gave me A, the sample path. Okay, so that is the path we took. So one summary of what we did so far could be thought of as that path. Is it clear so far? There's a different way to think about this path. They're all equivalent, okay? The different way to think about this path is I'll give you a trajectory, and then from that trajectory, let me try to figure everything else out, okay? One trajectory approach could be the following. Hey, I'll give you the two endpoints and connect it in time by a straight line. This is the trajectory I want. And if I give you this trajectory, give me the velocity field and give me the density evolution. That's something else you can do. A third thing you can do, which is optimal transport, is the following. I will tell you a property of the velocity field. I want it to be minimum energy transport between these points. Okay, I will solve that optimal transport problem to get a UT. Once I get that, I can find the density evolution and the sample path. So there are multiple, given now you can see that OT, if you do OT, if you do what I'm going to do, flow models, if you do the stochastics, they're all different ways of approaching exactly the same thing. And we'll see that, and we already saw that they're all in some sense equivalent to each other. Depending on how you put these costs, it's all different rescalings of the score. That's because finally, Anderson's things says that you want to get from here to here, you need to be affine in the score. Okay, and whatever you do, you're going to come back to the same thing. So you come up with some other learning thing, which is what I'm going to talk about here, conditional flow matching. It's also going to be affine in the score. And we saw that in lecture 15 when we looked at rectified flow, the stochastic sampler. Okay, so now when you see sort of various types of methods in literature, you should realize that these are all actually different ways of approaching exactly the same thing. And they finally come back to only three things: the continuity equation, Bayes rule, and total probability theorem. Using these three, by just dancing with this, everything will happen. And today I'm going to do this dance. Okay, as I said, this is from this tutorial paper by 4. It has way more than what I'm going to cover, so I encourage you to read it as well.
That's an evolution, just the margin, right?
Yes, the evolution of the margin. That's all I mean by density evolution.
Yeah, get the whole.
You can join distribution of the trajectory. Anderson's paper actually does that. It is actually, I am looking at a very special case. It's back in 82, you can do this. In fact, the margin, even though I'm saying Anderson, 1969 or 68, somewhere then, the density evolution of the marginal, I think, was known. It's, the Russian, the Soviet scientist, okay, somewhere. I don't remember the paper. Bruce Hayek actually pointed out that paper to me at some point. Okay, but but it was for a more stylized model. Anderson's paper did this sort of joint, but we are looking at the sort of the marginal for this particular setting. Okay. Okay, so I'm not going to go through OT. If I have time, I'll do optimal transport at the end, but there are other classes which talk about optimal. But now you see where optimal transport fits into this story. I could, if I want to do an optimal transport, I will start from here and say some properties of this to find that. And once I do that, that is going to lead to all the other stuff. Today, I'm doing this. I'm starting from this and getting to these. Okay, and this is basically this. We are starting from this. All right. So this is the flow we want. And now we need to specify the initial conditions. We can say, so the initial conditions I'm going to say are I'm going to sample a Gaussian x0 from and x1 independently from q star. from the data distribution and find a path between those two. This is the coupling. So essentially, we are coupling everything together by sort of product of independent things. But you don't need to do that. That's what I'm going to talk about. You could go off on sort of bridges and things like that. So if you see this word bridge problems, what you're doing, you could basically sample a pair, x0 and x1. X0 is a low resolution image, x1 is a corresponding high resolution image. And this again goes back to a question Constantine was asking some point. So I could use such a pair of sample and find a path to transport from one to another and then go through this machinery. Okay, so this is a very general machinery, but again, there are only three, at the core, there are only three things happening: total probability, Bayes rule, and Fokker-Planck. Okay. And then the rest is using clever properties of what you have to actually get an algorithm. This is not an algorithm yet. This is a formulation. Okay. To get an algorithm, you need to do something. Okay, so I've defined a sample path here. And the question now is, given this sample path, can we learn what is the density, what is the PT and the UT associated with this? That's the question. I have 4 minutes left. So I will basically give you a quick primer of where I'm going to get without proving anything. And next time we'll go through this thing, just so that I leave on a sort of clean note. It turns out it's much easier, instead of dealing with the density and the densities, to deal with the conditional densities. Look at the conditional density at time given the terminal constraint. This is not a causal thing. Suppose I know x at time 1, the data sample is little x1. What's the conditional density? Okay, let's look at that object. Then you can write the continuity equation for that, and that implicitly defines a conditional velocity field. Because the density exists, I'm assuming that density is nice, and therefore the continuity, there is a probability flux. That means there must be a velocity field. So I'm defining this u here through this equation.
R1 is like the graph of x1 at time 1?
Correct. Correct. It's just a good. So this is my xt definition. If I sample one end of it, then I still have what is the conditional distribution of xt given x1 is fixed, is nothing but it's a Gaussian with this mean and 1 minus t whole square variance. So that's what I mean. So actually, there's a closed form expression in this case. Okay. So because the straight line path, I know, well, if I need deterministic path, if I specify both the terminals, I know the entire trajectory. If I specify any one point on it, then conditionally I can get a distribution. Choosing x1 gives a very nice distribution that everything is Gaussian everywhere. Okay. It also connects to OT because with Gaussian, some KL divergence will become quadratic and all sorts of things happen. But I'm not going down that road here. I'm just sort of, I'm doing one. That would be the OT road to get to this thing. I'm not doing that. Okay. I'm just starting from this. I fixed one endpoint, x1. Okay. Then we will see. I don't have time to do this now. We will write the density. We can using total probability theorem and Bayes rule. You can derive what UT must be in terms of these conditional things. We will see that. Okay. Next time. Once we get this UT as a conditional expectation, we will try to get a closed form expression through, again, realizing that the conditional sort of velocity field has a closed form expression. You can combine these things to get that the velocity field with this approach can be written as a particular conditional expectation scale. That's exactly what TDs is too. Okay, score was affine in conditional expectation. Now you see the score is essentially popping up even this way too. Okay, and then you can continue and develop loss functions, all this. But anyway, next time I'll restart from this, talk through this, then come to RF inversion. That's my next lecture. Thank you.